Okay, so I'm going to go ahead and launch our first poll now that we are starting our little webinar. So the first poll that we're going to take a look at is just getting some data about how far along you are with respect to Akka.net. So we'll go ahead and run this in the background. We have a second poll that we're going to put up in a little bit about which monitoring and tracing systems that your company or team is currently looking at using. So I'll go ahead and leave that out there for everybody. And we will go ahead and get started in just a moment here, since we're a little early. Okay. Yep, thank you very much for the notification windows. All right. Well, in this case, we will go ahead and get started. So if you haven't answered that poll, please go ahead and do so. In the background here, the poll is about how far along you are with using Akka.net, what platforms you're looking at using, what environments you're going to be deploying into, and so forth. So today's webinar is a subject near and dear to my heart. We're going to be talking about Akka.net DevOps, how to perform systems monitoring, tracing, and alerting. Now, for our table of contents here, the first things that we're going to cover today is talking about what's the difference between observability, which is a relatively new term in our industry, versus monitoring. What are the differences between these two? Next, we're going to talk a little bit about Akka.net metrics and data. What are some of the metrics you actually want to pay attention to, and what are some of the pieces of data you want to collect inside your observability stack, which we'll talk about in step 3. And then we're going to talk a little bit about dashboards and health checks. So how should you try to arrange all of your information so your team can kind of manage the health of your Akka.net applications? What are some of the health checks and alerts you're going to want to set up? And then finally, we're going to go ahead and end today by talking a little bit about distributed tracing, which is basically how we can go about debugging a running Akka.net application that's actually up in production without needing to necessarily know what the pattern of end user behavior is before we start. Now, let's take a little look at our poll results so far. I'll go ahead and end the poll here. I'll share the results. So the results in terms of our poll, how far along are you in usage of Akka.net? So it looks like about roughly half the attendees today are in production with Akka.net already. Then we have kind of spread out across the rest of the long tail here. Developers are in a proof of concept or development stage, people who are evaluating it, and then folks who are just fans of Akka.net. Now, in terms of the platform distribution, looks like most of the people in this room are using .NET Core 3.1. Incidentally, that is also what Petabridge is using inside SDK Bin, which is one of our cloud services that is built on top of Akka.net, and also the same observability stack we're going to be looking at today. But we have a couple of bleeding edge users on .NET 5, and we also have a fair number of users who are still using .NET Framework. Then if we look down below, looks like we have a pretty even distribution of users who are running on premise, on the cloud, Kubernetes, and on Windows and on Linux. So I'll go ahead and stop sharing that so everyone can see what is on screen. Okay. So the next thing that we're going to go ahead and take a look at, and by the way, if you have any questions during the course of today's webinar, please go ahead and just ask them in the Q&A area of Zoom chat. I'd be happy to take those and field them as appropriate. But let's go ahead and dive into our material. The first of which is contrasting observability with monitoring. So monitoring is a very old practice that's been around since really the onset of web applications. Monitoring is a technical solution that allows us to understand the current or previous state of our system. So it allows us to understand what's the error rate, what's the level of CPU utilization, how many concurrent users do we have inside the system right now, all sorts of helpful metrics that kind of give us the ability to operate our application. Observability is the new entrant into this application and performance monitoring space. Now, there's lots of observability solutions that are available right now. We're going to go ahead and cover a couple of open source ones as part of today's course, but there's literally dozens of providers. Observability is less about being able to quantify the performance of your current system and more about the ability to query the system that is running right now without needing to know what the patterns are defined in advance. So, for instance, the biggest facet of observability is probably going to be either log aggregation or distributed tracing. It allows us to tell a story about how an end user's request was actually processed. And so, the role of both of these technologies are a little different. Uh, in the context of Akka.net, we're going to use for our monitoring solution metrics and alerting primarily. So we're going to go ahead and quantify the performance of the system. We're going to quantify the load that's on it, and we're going to visualize that using a dashboarding tool like Grafana. But the really important facet of monitoring is the ability to proactively notify the operators of the software system when the health degrades or when resources start getting exhausted. So, for instance, one of the metrics that we're going to be taking a look at in the context of monitoring is we're going to look at the number of unreachable nodes in an Akka.NET cluster. That represents a health degradation inside our system. But that's not enough to fully monitor it. We also want to pay attention to things like our CPU, our memory utilization, maybe our disk utilization, and we want to go ahead and keep track of that as well. So the next bit is observability. And this is where tracing and also petabridge.command, which we're not going to cover petabridge.command too much today, but these allow us to go ahead and query the actual running behavior of the system and see how things actually performed, end to end for an end user. So rather than telling us, let's say, the total number of end users inside a system, these observability tools might tell us, here's all the steps an end user's request took between them hitting the front end of our application and them actually receiving a response back. And that might include a bunch of inter-service calls. That might include a bunch of messages being processed by actors. And it might also include things like database queries behind the scenes. So the role that both of these technologies serve is a little different. Monitoring is about operations. It helps us assess the state of our services as they're experienced by customers. And it also allows us to keep track of key business and system metrics as well. So, a good example of a business metric we might want to pay attention to might be our end to end latency. Because the higher that latency gets, the lower our conversion rate might be if we're trying to sell products to customers on our website. But really, this is kind of meant to help us quantify the experience from the end user's point of view and let system operators know when we might need to do things like scale up the number of hardware resources we're using to serve a end user, or potentially there might be disasters that might occur, such as a shared resource becoming unavailable, like a database or a cloud file system. Monitoring is designed to help us know that so we can get out in front of those problems before it affects large numbers of users. Observability is more of a development concern, where really the goal is to kind of help understand why and how our system performed the way it did. As I'm going to put it a little bit later in this presentation, observability is really meant to resolve arguments among your engineering team. That's kind of the big overriding purpose of it. So we use the term DevOps a lot, but this is really where the both halves of it kind of come together from an observability and monitoring point of view. So that monitoring is about operations and observability is really about development. So we want to have both halves of these covered in the design and deployment of our systems. Now, what do we actually want to measure inside an Akka.NET application? What are the key metrics that can help us understand how well Akka.NET is performing in the greater context of our application? Well, I'm going to go ahead and include the big picture for you because Akka.NET usually only makes up a component of your software. It's not the end-to-end delivery system. It's just one piece of it in the same way a tool like Kafka or RabbitMQ might be one piece of your total experience you deliver to your end users. So we want to pay attention to some high-level metrics. These are the things you pay attention to for every type of application, whether it's using Akka.NET or not. And these are our hardware constraints. We want to know about the total amount of CPU utilization and the total amount of memory consumption. And probably I should also include in here things like disk and network utilization as well. These metrics, if we start running out of any of those resources, means our application is going to tip over and become unavailable. So typically, when you want to architect something like auto scaling in a cloud environment, these are almost always the metrics that your system keys off of, because this indicates that you're starting to run out of some physical resource you need to keep up with demand. Or you might be over provisioned and you might be able to get away with reducing your hardware footprint in order to save cost. So that's one big set of system metrics that aren't really specific to Akka.net, but nevertheless, we still want to pay attention to them. Now, next are our Akka.net metrics. We want to go ahead and keep track of the total number of actors we have by implementation type. This is going to be really useful. I've got another slide here that kind of explains why. But this helps us sort of understand how our application is currently being utilized as a result of the traffic being put on it. We also want to keep track of actor crashes, what's causing our actors to throw exceptions. This gives us an indication that there might be something wrong with a new deployment of our software, or possibly that a shared resource we're depending on has become unavailable. And then we also want to pay attention to message throughput. This tells us how quickly our actors are processing their workloads. With this information, we can go ahead and understand how responsive our system might be. And in the event that, let's say, one deployment of our application is significantly slower than another, that message throughput metric will help us observe that in real time as the deployment gets rolled out in either a development environment or more disastrously being rolled out to our actual live users. But nonetheless, that's why you want to have it. We also want to pay attention to the logging statistics coming out of Akka.net. In particular, we want to really keep an eye on the types of errors and exceptions that are being raised. One of the biggest sources of availability problems that you're going to have is typically when a deployment goes bad, meaning that, let's say, multiple services are being deployed simultaneously, and there might be some serialization problem, a shared resource problem, a configuration problem, all sorts of things that can go wrong. Ideally, we'd want to go ahead and resolve all of this via staging environments and development environments. But nevertheless, we still want to have a safety net in the event that we don't catch this before it goes to production. That's why keeping an eye on these is very helpful. It can tell you if messages are being dropped as a result of serialization issues. It can also tell you what types of exceptions are being raised inside your system too. So you want to keep a really close eye on that. I should also probably mention on here, keeping track of the numbers of dead letters and unhandled messages is a good idea as well. That's another thing that we can kind of keep an eye on via the logging system in Akka.net. Finally, if you're using Akka.cluster, which I assume many of the people attending this training currently are, you want to keep an eye on the actual health of your cluster itself. Namely, how big is it? How many nodes are all currently in an up state, which means they're able to access each other. But we also want to keep an eye on the number of unreachable nodes. And ideally, we also want to keep an eye on the number of nodes in terms of how reachable they are or whether they're available or not. We want to also do it by the role they have inside the cluster as well. So these types of metrics are things we'd either gather from a library like Phobos, which we're going to talk about, or you'd want to go ahead and have some way of publishing some of the events you can subscribe to in Akka.net out to an external logging or monitoring system. So a lot of the data that you can capture via Phobos in here, you can also capture via your logging system. And I'm going to show some of that using Serilog Seq, which is a log aggregation platform today. Finally, we want to take a look at our end-to-end metrics. These are the ones that help us understand how we're impacting our end users. So in particular, the one we really want to keep an eye on is our latency. When latency goes up, that tends to be an indication that either we are running out of some resource or there's a bottleneck that's formed somewhere inside the system. Bottlenecks are a harder problem to solve than resource constraints because typically that means there's an engineering problem. But nevertheless, we want to keep an eye on that. And so we tend to use histograms, which go and quantify the end-to-end performance in terms of quantiles. So the one that I typically pay attention to in our organization is called the 99th percentile latency. This is the upper bound of latency we can observe inside our system. It means that 99% of users had a better experience than this group. So this group had the absolute worst latency. If you've been working in ASP.NET for a long time, these would be the users who hit IIS when the app pool was being recycled. So they had to wait 30 seconds for their request to come back. The lower we can get that 99th percentile latency, it's going to go ahead and flatten the curve of all the other possible latencies underneath it. So that's why that one's a really important one to keep an eye on, because they're kind of the outliers in our system that determine what the maximum upper bound on latency is. Finally, we have our observability stuff. So all of this data so far is really for like the system operators. This is for the developers. We want to keep an eye on all of the traces and logs. In particular, we want to go ahead and do this when something goes wrong inside our system. All right, so we have our first question here. We go ahead and move this off to the right. Performance question about Phobos. I will go ahead and answer that at the very end today. All right, now, why do we have these metrics? Well, we have these system metrics, like I mentioned earlier, because they tell us if a resource constraint's about to become a problem. So we can either handle that by scaling up or down, or we can go ahead and let's say if there's a vertical scaling issue, we can try to reprovision some of our hardware. These metrics about keeping track of the number of actors inside our system tell us how many entities of X type, where X is your actor type, are doing Y work, which is your message type. So this kind of helps us quantify where's the load occurring inside our system. Now next, we also want to track sources of error and sudden global or local changes in error rates. So a global error rate change is the worst kind. It means that some shared resource that multiple services depend on has failed in some way. And that's starting to have side effects in many different parts of the system. The most classic example of this would be something like a database getting so busy it can't respond, and you'll start seeing a big surge in Okta persistence errors. That would be an example. But you also want to keep an eye on localized changes. Where, for instance, if we're rolling out a new version of an application service and we see the one node has a giant spike in error rates, well, it might tell us that there's some sort of incompatibility between the new code that's being deployed and the old code that's still running in the other services or even the same service inside your cluster. And we should probably go ahead and do a rollback as soon as we can. Our cluster metrics help us detect all sorts of insidious network problems, like a split brain, a dead node, or also potentially issues like instability in the cluster as a result of could be a set of, let's say, unobserved task exceptions that crash your processes. Could be potentially a problem with your infrastructure that's managing your cluster, or it could also be as a result of some of these system metrics too, where things like CPU utilization and memory consumption start getting so high that these nodes become unable to respond in a timely fashion to the requests they're being sent. And that would go ahead and start to show up eventually as a reachability problem. Now next, the latency and some of the end-to-end response metrics that we want to keep an eye on. Well, like I mentioned earlier, these help us quantify the experience from the end user's point of view. These are probably your most, if you only had to pick one group of metrics, these would probably be it. They can kind of tell you the story of what's going on under the covers here. They don't give you quite enough detail to figure out how to actually troubleshoot it though, which is why we have all these other metrics. But they help us understand what the end users are going through. So these are probably our most critical metrics. Finally, as I mentioned earlier, the observability metrics are primarily for solving arguments among your engineering teams. They let the developers and the site reliability engineers and so forth understand what it is that actually happened inside the system and what might have caused some of the problems end users were experiencing when users started receiving HTTP 500s or maybe when latency reached an unacceptable upper bound. So these are what we want to pay attention to. Now, in terms of how we're going to use each of these metrics, I've gone and color-coded the same diagram. Our metrics that are in red, we're going to use for alerting and auto-scaling. So these are primarily going to be keeping track of things like resource utilization, error rates, and also the end user experience. The green metrics are mostly for the operators to kind of understand how traffic flows through their system. So for instance, if it turns out that there's one particular actor type that has a much higher, let's say, total message throughput than everyone else, and there's a sudden change in that throughput, that might be what's responsible for the increase in latency between deployments. So that's an example of one type of issue. Next, the blue ones are for tracing and debugging. This data is not meant to kind of fire, let's say, not necessarily meant to go ahead and produce alerts or meant to kind of let the site reliability engineers know there's a problem. It's really meant to help the engineering team after the fact understand why these other metrics were the way they were. And so this is kind of meant for debugging purposes more than anything else. So that's the way we're going to go ahead and use this set of metrics. Now, let's go ahead and actually talk about the technologies we are going to use for doing this. And I'm going to start this with a disclaimer. There are dozens of tooling combinations, and the ones that we're going to show you on the screen are not right, and different configurations other than the ones that we're showing are not wrong. We picked all these because they're largely open source, so it's easy for us to make demos out of them, and they're also fairly reliable, widely accepted tools in the industry. So there's a lot of ecosystem support for each of them. And in particular, these tools can work in environments like self-hosted on-premise software, Kubernetes, and a public cloud environment, you name it. But these tools also easily integrate with Akka.NET, ASP.NET Core, and other sort of popular frameworks for building applications in the .NET ecosystem. So that's why we picked these. If you're using something different, in fact, this would be a good time for me to launch the second poll, which I will go ahead and do right here. Go ahead and relaunch polling. Nope, don't want to do that. I want to go to polls. Yeah, there we go. All right. So I'm launching a second poll right now, which is all about which telemetry choices does your team use? This will be helpful for us in terms of the way we develop Phobos, because it lets us know what tutorials and material that we should go ahead and produce. But it's also just generally good to know this for the ecosystem. I see there's a question in YouTube. How can we participate in the poll? You need to be in the Zoom meeting for that, unfortunately. So I'll go ahead and leave the polling up for just a second here so we can go ahead and answer some of these questions. And then I'll go ahead and introduce our observability stack. We're going to be using Phobos, which is a commercial library that Petabridge sells for Akka.NET. It's designed to automatically instrument metrics and tracing into your Akka.NET applications without the need for adding additional code. And Phobos is built on top of another popular .NET library called App.Metrics, which is a really reliable tool for being able to export data and metrics to lots of different sources. So that's what we have going on down there as far as our instrumentation libraries go. Next, we're going to use Prometheus for actually collecting all of our metrics and turning them into time series that we can visualize into all sorts of charts and dashboards later. So Prometheus is, we're going to spend a little bit more time covering it in the next section here, but it's a highly accepted industry standard. Prometheus's metrics format is also what's responsible for defining the metrics format for the OpenTelemetry standard that's going to be included in ASP.NET Core 6 and .NET 6 by default when those release. So Prometheus is a fairly kind of widely well-known open source project for gathering metrics. Next, we're also using a tool called Node Exporter. This is a Prometheus plugin that's really specific to Kubernetes. That's what we're using that for there. And let's see. Let me go ahead and check the polling in just a second here. And then finally, we're also going to use Grafana, which is a very popular open source data visualization and alerting platform. And we're going to be spending quite a bit of time using that today. Let's go ahead and end the polling real quick. And I'll share the results on screen for just a moment. So in terms of the people who are attending our training today, these were all multiple choice questions. So people could select multiple options here. Looks like most of our users are using centralized log aggregation. And there's a small number who are using alerting, a small number who are using metrics, a reasonable number who are using dashboards, and an equal number who are using distributed tracing. By the way, we're going to be using all of these today. Now, in terms of platforms that people are using, we currently have, a bunch of people using Prometheus, a bunch using Application Insights, a bunch using Seq, a bunch using the Elk stack. This is Elastic, Logstash, and Kibana. And we also have a bunch who are using Grafana. Now, let's see, I've got a question in chat about where can we go to participate in this webinar. I will go ahead and drop a link to that real fast. Go ahead and copy it and share it with them so they can answer some of these questions. Okay. So it looks like we're all using a wide range of tools minus Google Stack Driver, which tells me there aren't very many Google Cloud users in here. Google Stack Driver is basically application insights, but for Google Cloud. All right, good. That's good to know. So we're going to spend a bit of time going through all these tools today for the metrics side of the equation. The other side we're going to take a look at is tracing and logging. So again, we're going to use Phobos plus the OpenTracing standard. Specifically, we're going to use Jaeger, which is a open source distributed tracing system that is highly decentralized, easy to query, and it's relatively fast. Right now in production, my team here at Petabridge, we actually use application insights for distributed tracing. So we are not currently using Jaeger in production. We are going to be changing that though. And we do use Serilog and Seq, however, for capturing structured log events from both ASP.NET Core, from Standard Out, and Akka.NET. We go ahead and gather that data and we analyze it in Seq and use that to power alerts that let us know when something goes wrong in production. So these are some of the tools and technologies we're going to be looking at today. Now let's see, we have a couple of items in chat. Looks like these are just chat questions mostly. All right. Okay. First question was single choice. My bad. I'm sorry I got that wrong. Um, so let's talk real briefly about how we're going to go ahead and actually configure all of this. Now, I'm not going to go through belabor the point and spend too much time talking about how we do installation. But long story short, this is just going to take some NuGet packages. We're going to go ahead and install our logging stack first. So I'm assuming that you're all using Akka.NET. We're going to install the akka.logger.serilog package, which allows Akka.NET to consume Serilog internally. And then we're going to install some logs for Seq, which is the aggregation system we're going to export all of our structured log data to. Next, we're going to install some of the App.Metrics libraries. We're going to add their ASP.NET Core support. That way we can gather some of that end-to-end performance data directly from App.Metrics. And we're also going to go ahead and install the Prometheus formatters. So Prometheus can go and gather that data. Next, we're going to install Jaeger, which is our tracing driver. This is what's going to allow us to take all of our distributed tracing data and put it in one place where developers can query it. They can also search. So for instance, I'll be able to, and I'm going to demonstrate all of this. You can go ahead and search for requests that have a specific tag in it, or requests that failed with a particular type of error code. Jaeger is going to go ahead and provide us with sort of an interface for exploring all that information, which will be very useful for your development and site reliability engineering teams to go and understand why or how things went wrong. We're going to go ahead and install the Phobos.actor.cluster NuGet package. This is what's going to instrument our Akka.NET actors with all these metrics and all this tracing under the covers. And then we're also going to install this OpenTracing.contrib.NET Core package. This is what's going to go ahead and take data from ASP.NET and include that inside our traces. One of the really important parts of distributed tracing is to be able to tell the complete end-to-end story of what happened. That means we need to connect the dots between what happened in ASP.NET and what happened inside Akka.NET. And that's what this library is going to help us do. It's going to make sure that the trace starts as soon as a request comes into our little web application that we're running. And then it's going to go ahead and connect the dots with all the activity that happens inside our actors, which is what the Phobos library is going to do. And then finally, if you want the ability to go ahead and query your system at runtime with petabridge.command, you'll want to go and install both of these packages under the covers as well. Okay. So if you want to follow along with the demo that we're going to use today, you can go to github.com/petabridge, petabridge.phobos.web. You will need a Phobos key to go ahead and actually work with this. But theoretically, you should be able to go ahead and run a lot of this without necessarily having Phobos installed. And I can walk you through how to do some of that. But this is the sample that we're going to go ahead and run. It's a really simple web application. And the way we're going to go ahead and build it is I'm going to go down to my little command line that I have here. And if you want to go and run this sample after you get a Phobos key, you'll just type build.command docker. This will go ahead and build some of the latest Docker images behind the scenes. And that shouldn't take terribly long. Go ahead and let that run. All right, that's going to go ahead, finish doing a little bit of NuGet restore. Going to go ahead and build my little Docker image here. And then inside the Kubernetes folder, the Kates folder here, I type this deploy all command. This is going to create a local Kubernetes namespace on my machine, and it's going to go ahead and install 3 instances of this Phobos web application together, along with all of our monitoring infrastructure. Now you may notice I've already been running this for about 3.5 hours so far today, so I've already have some data pre-populated, but nonetheless, this would go ahead and work right out of the gate, and it would go ahead and start populating data into all of our systems. Now, first thing I'm going to go ahead and show is I'm going to pull up our source code for this sample. The first thing that we want to go ahead and do as part of building our observability stack is we want to go ahead and get Serilog added. And we're going to do this before we actually run startup.cs. We're going to go to our program.cs where we create the host builder for ASP.NET Core right here. And I have a little extension method I wrote called configure Serilog logging. I'm going to go to my declaration here. This is going to go ahead and clear the other logging providers, and it's going to add the console provider back, but it's also going to go ahead and add Serilog and the event source logger. So this will go ahead and make sure that all the events that are captured using the normal iLogging interface from Microsoft.extensions.logging, all that data is going to get piped to Serilog now, which means we can query it inside Seq, our sort of logging and aggregation system. And this little static helper class I wrote right here is going to help me do a couple of things. First, Seq uses Serilog, the logging library, uses an approach that we call structured logging. It might also be called semantic logging. This means that rather than viewing your logs as a string, where you basically have to go ahead and try to delimit little pieces of it out by using regular expressions and parsing, Serilog actually breaks those logs down into contextual events that have properties that are already sort of explicitly carved out. And therefore, a structured logging system like Seq or the Elk stack can go ahead and immediately aggregate this data together, can filter it, and can essentially interpret a lot more data from your log statements than it could if it was all being done on the fly via, let's say, just strings with new line endings at the end of it. So in this case, I'm going to go ahead and create a logger configuration for Serilog, and I'm going to go ahead and pass in some custom properties. One property is the pod name, which I'm going to go ahead and use with my service name here. This helps tell me sort of which service produced this data. I'm also going to pass in my ASP.NET Core environment in here. We use this in production at Petabridge to help us separate, because we have logs from our development QA and production environment all going to the same log aggregation system. This helps us essentially filter those, is what this is useful for. And then we also know the name of the service. So we know the name of the service and the instance and each instance of it. So if I have 5 different pods all running as part of the service, I can query their data individually. And by the way, this will work for all the data that ASP.NET and Akka.NET records without us having to decorate any data at all inside any of our actor classes. And this is the sort of format that this is going to write out to for when it goes to the console behind the scenes. Next, I have a little feature flag right here to check to see if Seq is enabled or not, and that's done by checking for the presence of 2 environment variables, I believe. Yeah, Seq service host, Seq service port. If both of these environment variables aren't defined, Seq is disabled, so we don't bother trying to export any of this data to it. We're going to talk about why we're doing this in just a second, but it basically comes down to a best practice that you want to go ahead and make sure that your APM infrastructure for monitoring your application's performance is never a critical dependency your application can't start without. We ideally want to be able to monitor everything in our system, but it shouldn't be a requirement. In the event that we have, let's say, developers who want to be able to spin things up locally and try it out in Visual Studio, we should be able to support that. That's why having little toggles and feature flags like this is really useful. Guarantees that I can go ahead and send this repository to one of my developers. They can go ahead and clone it onto their system and get it up and running without any trouble or without having to go and create a very elaborate local environment. That's what we're trying to avoid here. So this is Serilog in a nutshell. The way this is going to get consumed by Akka.NET, by the way, is this little line of HOCON configuration, the Serilog config. This tells Akka.NET to go ahead and load the Serilog logger, and it's going to grab this static configuration right here and consume that as soon as it starts. And then inside my little Akka.NET service, if I scroll down, let's see, that should be, oh, you know what? That's actually my startup.cs. We're going to go ahead and basically call this use Serilog extension method, which is just going to inject that Serilog config in the back of the other HOCON that we're going to use to configure Akka.NET down here. So that's what that's all about. Next, for the other parts of our APM stack, all this is going to be configured inside startup.cs. So in our configure services method right here, we're going to go ahead and use the OpenTracing contrib package to go ahead and automatically trace all the requests that pass through ASP.NET Core's pipeline. And so I'm going to go ahead and customize the way we render those names in OpenTracing. I'm also going to have us ignore any traces that come from metrics. This is the endpoint that Prometheus is going to scrape for gathering its data. And this will create a ton of noise inside our tracing system if we don't do that. So we're going to go ahead and ignore that. You might also want to include things like health checks that occur in here too. So for instance, in production, we have a what's called a readiness check. We ignore that inside our tracing system as well. Next, we're going to configure App.Metrics to go ahead and record our quantifiable data about how the application is performing. Then we're going to configure Jaeger to do tracing. And then finally, we're going to stick all this inside Akka.NET and ASP.NET. So let's take a look at App.Metrics real fast. Go to definition here. So I'm going to go ahead and make some calls. These are extension methods provided by the App.Metrics ASP.NET integration. So we're going to go ahead and say we want to add the middleware for tracking all of the request response times and status codes. I'm going to go ahead and define my metrics output right here. And this is important. I'm going to go ahead and say I want to go ahead and have my metrics add a global tag called host, and that host is going to be my host name. This is going to allow me to go ahead and differentiate which hosts produce which metrics. So I'm going to pass that in. I'm going to go ahead and pass in a default context label. This kind of defines the context label for all of my personal metrics. And then I'm going to go ahead and also just say that I'm going to enable app.metrics to go ahead and record, and I'm going to go ahead and enable it to report. And I'm going to specify that all my output should be shipped as Prometheus plain text. App.Metrics supports like a dozen different metrics targets, so I could go ahead and add things like InfluxDB here if I wanted to. And finally, I'm going to go ahead and say we need to add some metrics endpoints. These metrics endpoints are going to be visible if I go to my local copy of the running application here, which is localhost 1880, my metrics are going to be visible if I go to the /metrics URL. And this is all the data that Prometheus is going to gather, by the way. So I'm basically just telling app.metrics, host all of my data here. So Prometheus can go and scrape it and include it in its time series data that we're going to use to power our alerts and monitoring down the road. So that's app.metrics in a nutshell. This call you actually don't need if you're running ASP.NET Core. So I could actually disable that and this would work fine. If we take a look at Jaeger down here, I'm going to go ahead and basically add this iTracer. This is the OpenTracing interface here. This is what Phobos needs to do tracing. And this is also what OpenTracing needs in order to trace ASP.NET Core. I'm going to go ahead and pass in some environment variables that I defined a bit earlier. But I'm going to go ahead and use to build, build my sender, which is going to occur right here. So I believe we're using the Jaeger agent port and Jaeger agent host to go ahead and create a UDP sender. That way we don't get any errors in the event that no one receives our traces when we're running by default. Because UDP is a connectionless protocol, so we're not going to get any hosts not found errors or anything like that. The packets will just go across a bridge to nowhere if that occurs. So we're going to go ahead and basically build a little Jaeger tracer down here. I'm going to go ahead and make sure that my service is named after my startup assembly. So if the name of this application is petabridge.phobos.web, that's going to be the service name that shows up inside my system. We'll talk a little bit about sampling a bit later. This is a good practice for extremely busy systems. Sampling is designed, so tracing is expensive because of the amount of text it has to export. Jaeger comes with what's called a dynamic sampler, where based on the busier your system gets, the fewer traces it's going to include inside the sample. That's designed to make sure that the majority of your resources go to actually serving your end users, not tracing what they did. And this line is really important right here, this actor scope manager. This makes sure that we can properly correlate traces that occur inside our actor system with traces that occur outside the actor system. And this is part of the Phobos library. We have an extension method as part of Phobos that'll let you wrap any OpenTracing iTracer with a scope manager. So for instance, all of our users who use Datadog need to do that because Datadog, for whatever reason, does not let you pass in your own scope manager when you're using their OpenTracing instrumentation. So we'll go ahead and return this, and this tracer instance will get used inside every actor in Akka.net that's enabled to trace, and inside every ASP.NET request. So we're going to go ahead and add that. Finally, at the end, we're going to go ahead and configure Akka.net, and we're going to use the service provider that we just registered all these dependencies in, and we're going to go ahead and get our App.Metrics root from App.Metrics and our tracer that we just configured. And we're going to go ahead and use this class in Phobos, this Phobos setup, to bind our metrics root and our tracer. And then we're going to pass in our Hocon configuration, and we're going to enable Phobos at this line right here, Phobos provider selection.cluster. If I disable this line right here, I could turn Phobos off without any issues at all. And then I'm going to go ahead and pass this into my actor system and return it. And this actor system will be run inside my little Akka service in the background as a hosted service. That's kind of the best practice for running Akka.net and ASP.NET Core. We will be making a YouTube video on that in the next couple of weeks, so no worries about that. But that should give us everything we need to go ahead and run our application. Finally, I'm going to go ahead and tell ASP.NET that I want us to go ahead and use all of App.Metrics' middleware and to expose App.Metrics on that /metrics URL. And then finally, I'm going to go ahead and create a little route where every time we make a GET request to the index, I'm going to go ahead and use a tracer to build a span. And I'm going to go ahead and ask this router forwarder actor this message. And I'm going to go ahead and expect a response back and write it out on screen. And this is what's happening when I view this page. So that's the installation piece. Now, so we just talked a little bit about how to actually instrument our application. And by the way, if that seemed complicated, this allows us to go ahead and capture all the logging, tracing, and metrics data we want. And it's all aspect oriented, which is one of our best practices that we recommend. So best practices for managing observability is to make sure that observability infrastructure should not be a critical dependency. If Seq was not available, for instance, inside our cluster, we would not want to crash or stop our application from starting up. Or if Jaeger wasn't available, we would want to basically force the application to fail and exit inside our startup method. So that's where toggles can be really helpful, to go ahead and enable and disable observability on the fly when it's necessary. This will make the software developers on your team happier. The other thing you should do is try to prefer aspect-oriented instrumentation. Instrumentation that can be injected inside your stack, inside your startup method, without you needing to go and decorate every single controller, every single actor, every single message. This is a much cleaner way of doing it. Is that A, makes it easier for you to go ahead and change your observability stack, which you might need to do as your applications grow or as your environments change. But B, it also just kind of reduces the technical debt that observability is going to introduce. So aspect-oriented instrumentation is the way to go. That's one of the reasons why we developed Phobos, was to go ahead and provide that for Akka.net behind the scenes. None of the actors that we're going to go ahead and send messages to have any tracing code in it that is needed to render any of these metrics or graphs. The last bit of really critical advice, and this is just as important as how we instrument our applications, is our observability structure, meaning all the data inside our stack needs to be immutable. This means that every single piece of infrastructure we need to run observability inside our system, observability and metrics in this case, is we need to script all of it. So here at Petabridge, we use Pulumi and a combination of Helm charts and Kubernetes config maps to program everything from the dashboards that are installed into Grafana by default, to go ahead and configure how we store and persist tracing data. We even try to go ahead and script things like the alerts and the notification channels that our alerts fire to when we can. So that way, no one on our team has to necessarily remember how to configure everything when we need to set up a new environment. That's all institutionalized inside the scripts that we run, which makes it a lot more agile for us to be able to make changes. And it also is kind of self-documenting in a way, where if you want to understand how these things fit together, even if there's no documentation is obviously better, but in the event that there isn't any, which there often isn't, having reviewed a lot of our customers' applications and deployments, at least you can go ahead and read the script and see how things get wired together. So without any further ado, let's go ahead and take a look at what the actual observability, tracing, and logging data really looks like inside a running Akka.NET application. So the tool that we're going to use as kind of the wedge for all this stuff is Grafana and its alerting capabilities. Grafana is very powerful. It works with a lot of different metric sources. You can even hook Grafana up to cloud-hosted sources like Application Insights if you want. We're going to use Prometheus for all of that. And we're also going to use this brand new Grafana dashboard that I just published yesterday, which is going to use all of the default Phobos metrics to visualize most of those operational and business metrics that we care about with respect to Akka.NET. So I'm going to go ahead and run a little demo that shows how you can install that inside a Grafana instance and instantly kind of visualize the performance of a running Akka.NET application. And you can see a little screenshot of what that looks like right here. We're going to go ahead and do a live version of that in just a second. The second tool we're going to look at for doing dashboards and alerting is going to be Seq, a log aggregation platform. Seq is built by the makers of Serilog. There's a free version that's available. We use the paid version here at Petabridge so we can support a larger number of options for different types of alerts and have multiple concurrent users and authentication and all that good stuff. But the free version of it is pretty good on its own. So we're going to go ahead and use that to query and group these logs together via their semantic properties. For instance, I could go ahead and write a query that's going to aggregate all the logs by their error code, or by the host where they came from, or by the environment they were deployed into, and so forth. And we can transform these logs into metrics by accumulating them based on these properties over a very sort of, let's say, finite window of time. And so this is what one of our Seq dashboards looks like, for instance. So let's take a look at a little demo of all this. So the first thing I'm going to do is I'm going to go ahead and pull up my Grafana instance. So by default, my Grafana instance in this demo actually comes with a couple of dashboards right out of the gate. These are scripted into it via a config map that Grafana is going to mount in Kubernetes when it first starts. So I can see I've got some operational metrics here. It looks like the way CPU utilization is being queried here might have been broken in the latest version of Grafana. So I might need to go ahead and grab a new chart here. But this is how I take a look at my operational metrics. But the really cool feature of Grafana is the fact that it has this rich ecosystem for being able to go ahead and import all sorts of custom charts that are made by other developers. So in this case, we're going to go ahead and pull up this Akka.NET clustering and Phobos metrics chart, dashboard that is built on top of a Prometheus data source. So to install it, all I have to do is copy this ID to my dashboard, go in here, I paste that, and I click load. Then I just need to select a data source that I'm connected to. In this case, I'm connected to this Prometheus data source, and I hit import. And I can go ahead and see all this data that was queried live from Prometheus about how my system is performing. I can see that I have a 3-node cluster with no unreachable nodes. I can go ahead and take a look at all the different roles inside my cluster if I want, and all the different node addresses that are in it. By the way, so I had 25 nodes a couple hours ago. That's why there's so many in here. But if I wanted to query just this node, who I know is still a member of my cluster, I can go ahead and see all the logging activity specific to this node, or I can go back to seeing the logging activity for all of them, and I can see these values change here. I can take a look at, let's say, the total aggregate logging activity of the cluster. I can see what my, let's say, info and error rates look like. I can take a look at the exceptions that are observed in the log. So by the way, behind the scenes, my Akka.NET actors are periodically throwing exceptions. That's by design. That's to help make the demo a little bit more interesting. So that's all running by design behind the scenes. Next, I can go ahead and take a look at the total number of actors in my system. And I can see that there's a grand total of 7 live actors on all 3 of these nodes at any given time. And I can see that the total request throughput for these actors is about 2.8 requests per second in aggregate for the entire cluster. Now, if I take a look down here, I can see my live actors by type. And I can see that I have 3 of all these different types of actors alive. That's because I have 3 nodes that are currently live inside my cluster. If I filter this down to just one node, I can see that I have 1 actor of each of these types alive. I can also see that I've spawned 1,000 of these child actors and killed 1,000 of them. So these actors are being created on a per request basis, and they're being killed as quickly as they're being started. That's why this graph never really moves above 7, because these actors just don't live long enough to actually be measured between the sample intervals. I can see the actor types and the exceptions they throw here, so I can see why they're crashing. And I can also go ahead and measure the total actor message throughput by type. And I can see that the number of, so most of my actors are processing strings and info events. And that's because I have some actors in petabridge.command who are listening to these log events as they're being sent. And I can go ahead and see the actor message throughput by type as well. And I could drill even further into these metrics if I really wanted to. So this is our sort of our Grafana dashboard right out of the gate here. Now, where this is gathering data from, if I go back to our petabridge.phobos.web here, is it's gathering all this data from Prometheus, which also has its own little UI here. So I go ahead and write a query like Akka.NET. Let's take a look at Akka.NET dead letters. And I go ahead and say, I want to sum dead letters by Akka address. I go ahead and execute this. This is going to tell me that all 3 of these nodes, I have 72 dead letters on the first node, 109 on the second, and 70 on the third. So Prometheus is storing all this data in a time series database, and it's going to limit the amount of disk storage it has to use. But Prometheus is extremely resource efficient. The way Prometheus works is it uses a pull model for fetching your metrics, where Prometheus, if I take a look at its targets here, basically is aware of all these different little nodes inside my Kubernetes cluster. And it's going to go ahead and periodically send an HTTP request to scrape the data from the localhost 1880/metrics URL. And it's going to go ahead and consume this data, and it's going to match it against the data it's storing in its time series database. So that means that if you have a really busy system that's producing enormous quantities of metrics data, Prometheus is going to always consume that data at the same rate. All that data is being pre-aggregated locally inside your own process using App.Metrics. So it's very scalable, is one of the big benefits towards using it. Now, if I go back to my graph here, I can go ahead and watch in real time as things change. In fact, one thing I want to take a look at is before we keep going, let's take a look at some alert rules. All right, looks like I have a live request alert here. I should have an alert built into, if I go back to my dashboard here that I just installed, I should have an alert in here that I can set. In fact, yes, I do. I do have an alert set here. All right, perfect. Well, I'm going to go ahead and test this rule. Take a look at the state history. No state changes recorded. Got it. So this alert should be available. If I take a look at my alert rules, I still don't see it on here. Take a look at OK, not OK, no data, paused, pending. All right, well, maybe we don't have enough data yet. So I'm going to go ahead and try to fire an alert rule using Grafana real fast. And my notification channel I've set up for this is using Petabridge's Slack right here. So it's going to push a message into my little Phobos demo alerts room here. So let's see what happens if I go ahead and try scaling up my cluster, which I believe I could do right here. So let me go ahead and try scaling this from 3 nodes to 25. and we'll watch what happens in real time. I'll go back to my dashboard. We'll see that we're up to 4 nodes so far. We should also start seeing our logging activity begin to pick up. Nodes joining the cluster tends to produce a large number of logs. So yeah, you'll see these values are starting to tick up down here. We'll also start to see an increase in the number of nodes who are reporting live actors down here. That number is going to start to go up. And now we can see that we have 2 unreachable nodes. And if I mouse over here, I can see that we have, let's see, 6 nodes that are up, 2 that are unreachable. There's a little bit of latency here because it takes a bit of time to pull some of these values. But we're going to go ahead and see the cluster churn a little bit. And the reason why the cluster's churning, by the way, so if I go and take a look down here, I go ahead and run a little Kubernetes command inside my namespace. I can see that we're spinning up a whole bunch of processes all at once, and all these processes are all trying to network together and help form a cluster. Now, if I take a look at my alert rules, I still don't see that alert rule I imported firing on here. That might be an issue with Grafana, actually. So let me go ahead and try changing this. Change that to 1, save. I'll change that to 0 again and save that. Apply. There we go. Looks like that was an issue with importing the dashboard where it wasn't firing those alerts. Now if I take a look at my alert rules, there we go. This alert rule is going to fire periodically here. Now if I click in and take a look at it, the way I've defined it is we're going to evaluate this rule every 30 seconds. And if we have any number of unreachable nodes above 0 for longer than a minute, we're going to go ahead and fire an alert inside Slack. Now if I take a look in Slack here, you'll notice that the other part of our stack that we're running here, which is Seq, our log aggregator is actually also firing some alerts. So let's take a look at that while we're at it. So if I go to Seq real fast, oops, no, I do not want to discard. You know what? Sure, I will discard those changes. If I take a look here and I run this unreachable node signal, this signal, by the way, is just querying to see, do we have this text that appears inside any of these logs, marking node as unreachable. This is one of the automated messages produced by akka.cluster whenever an unreachable node is detected. And we can see down here that this node is marking, so node 17 is marking node 19 as unreachable. And we can see some of the properties that are being extracted from Serilog semantic logging system right here. We can see the actor path. We can see the environment. This is a development environment. We can see the log source. We can see the name of the pod, the name of the service, and we can also see the context. This comes from the akka.cluster cluster core daemon. So if I want to go ahead and take a look at, let's say, all of the messages that came from this pod, I go ahead and say find for this pod name here, and I can see that this pod has marked a bunch of other pods as unreachable. It marked Phobos Web 18, 19, 21, 22 unreachable. It looks like it did it twice. So this is an example of using structured logging to be able to go ahead and power some alerting inside of our system. And in fact, the way this system works is I have this little simple dashboard I set up right here, which I'll go ahead and edit, where I'm querying my unreachable nodes signal that I saved inside Seq. And I'm going to fire an alert every time the count is greater than 1 for longer than a minute. Every 5 minutes, we're going to go ahead and fire an error notification into this little Slack channel that we had installed. And I was able to go and set up this alert by going to Settings, Apps, and I installed the Slack notifier from NuGet. And I added a little instance here that has access to my webhook URL under the covers, and it'll go ahead and fire a custom event into this channel that I configured right here. Now, eventually, our cluster is going to stabilize. Yeah, here we go. We're at 25 up nodes now. So our cluster took a little while to form, but it did stabilize after a period of time here. So now we know that we've got 25 nodes. I can see the total number of errors we logged. I can see that we went from doing about 2 requests per second to about 17. And I can see all the different nodes in the cluster that have 7 actors that are all detected by Prometheus. So this is an example of our sort of monitoring stack so far, to be able to go ahead and observe some of the changes that are occurring as a result of our cluster shape changing in size. Now I can also filter by the role. I only have one in this cluster here, but if I had multiple service types, I could filter by this as well if I wanted to. So this is an example of being able to use dashboards and alerting pretty effectively to let us know when operationally something bad is happening inside our system. And in fact, I'm going to go ahead and scale this back down real fast because I don't want to run out of disk inside Seq or inside Jaeger, which is the next bit we're going to take a look at. All right, now let's talk a little bit about distributed tracing. This is determining how and why things went wrong. So for instance, we were just able to take a look at our dashboard and know that we had some unreachable nodes that occurred. And we took a look inside Serilog, or inside the messages produced by Serilog, and we saw that it was probably just a function of some connectivity problems as a result of so many nodes joining the cluster at once. Well, what distributed tracing is designed to help us do is help us understand, hey, if an end user was affected by that problem, what caused it? Could it have been affected by, let's say, could it have been affected, for instance, why could it have been affected by one of those nodes being unreachable? Could it have been because we had a database timeout and so forth? Distributed tracing is designed to help us answer those questions. So distributed tracing is all about preserving context between requests between services so that every single time, let's say, a user contacts our service, we start a trace for that request. And every subsequent request we make to either another service or an actor or a technology like a database, all of that data gets preserved and we can tie all those steps back together into one contiguous diagram. We also want to get detailed per operation data. We want to know what was logged inside each one of these services. We also want to know the context, for instance, in the context of our domain. A good example, we can append a custom tag to each one of these traces that might have, let's say, our company user ID attached to it. Or maybe it might have a transaction ID if we're trying to process, let's say, a bank transaction inside our system. We want to go ahead and make sure that data gets preserved as well. Now, distributed tracing also reports data out of band, meaning that spans, which are the individual operations, can all be recorded asynchronously and published to a tracing system like Jaeger without us having to wait for the entire operation to complete first. Jaeger will find a way to stitch all that data back together and turn it into something usable that we can explore. And then finally, we want to have some visualization and diagnostic tools. We want to be able to visualize the trace so it's easy to understand, and we want to be able to make the traces searchable. So we can go ahead and go looking for requests that had specific properties. For instance, a request that took longer than our maximum latency threshold, or a request that returned a 500 error, or maybe a request that had some other type of crash or exception to it that we want to look for. A good distributed tracing system will let us look for all these things so developers and site reliability engineers can answer those questions. And here's sort of a big picture of what the distributed tracing process looks like. We go ahead and let's say we have an HTTP request come in from a user into service 1. Service 1 talks to service 2. Service 2 talks to service 3, and service 3 talks to a database. In this case, we're using a Zipkin, which is another open source tracing system that's pretty similar to Jaeger. Well, this request down to the database is going to finish first. And so we're going to go ahead and get a trace with an ID of 1 and an operation ID of 4. And it's going to have an operation name, service3.db.query or whatever. Well, then the HTTP operation that created this database query will then complete once we serve our HTTP response back to service 2. And we're going to go ahead and record trace ID of 1, span ID of 3. And then service 2 is going to finish its operation. And then finally, when service 1 returns its response to the end user, it's going to record that operation. Notice the trace ID is the same for all of these. That's how our distributed tracing system like Zipkin or Jaeger is going to know how to correlate all this activity together. We're going to end up with a histogram that looks like this, where we can see that the end-to-end time of this top level request was 210 milliseconds, and that the request underneath it took 180, and the request underneath that took 140, and the database query took about 40 milliseconds. Well, one of the things I'd be able to tell by looking at this is, you know what? Looks like the bulk of my latency actually came from service 3 taking 140 milliseconds, an additional 100 milliseconds on top of the 40 milliseconds it took my database to run its query. This might tell us that we might have a serialization problem, where maybe the data set we're getting back is too large, and this service is taking a long time to format it into a response. That might be an example of a type of optimization we could send our engineers after if we see this pattern show up over and over again. So this is an example of how tracing is kind of designed to help tell a story of what's happening inside our system. So we're going to look at a demo of this real quickly before I end the webinar and take some questions. But the best practices for working with tracing with not just Akka.net, but really any .NET stack, is you want to go ahead and try to introduce tracing at the infrastructure level using Phobos or injecting into the HTTP request processing pipeline. This will help make sure that everything ties in together. You don't want to be responsible for making sure you add tracing headers to every single message that you send. That would get excruciating after a trivial number of different HTTP methods and messages. So you really have to do this as an aspect-oriented concern. You want to go ahead and make sure you're using the right scope manager. The default one uses async local under the covers. In Phobos, you want to go ahead and use the actor scope manager behind the scenes. And then finally, you want to make sure your logging infrastructure is going to inject all of the events it captures into the active span. Phobos does this automatically for Akka.net, and I believe the OpenTracing infrastructure does this automatically for ASP.NET Core. This is useful because it helps kind of form a more contextual picture of where those logs fit. So we're going to end up duplicating our logging data. It's going to live in both Seq, our log aggregator, and our distributed tracing system, but they kind of serve different use cases in each of those environments. In a system like Seq, for instance, the logging data is really used to help kind of troubleshoot where errors are coming from and how quickly. In a system like Jaeger, the logs are used to help give us some clues as to what was the system trying to do when this thing failed. And it helps us kind of organize it a little bit more efficiently for either use case. Finally, we want to try to use our tagging infrastructure inside OpenTracing to add domain-specific data to all of our operations that we record. So pieces of data your infrastructure isn't going to be aware of by default. So for instance, if you correlate, we have a lot of customers here at Petabridge that work in fields that have very high auditing requirements. You might want to go ahead and have your audit trail correlating ID as a tag you append to all these traces. Or maybe it might be a user ID or a transaction ID and so forth. This helps us search for, let's say, requests that affected a specific user's experience or a specific transaction inside our system. So let's take a look at a little demo of all this. So I'm back down to 3 nodes again inside my cluster. And I'm going to go to my little GitHub repo. And I'm going to click this link to launch the Jaeger UI. Now I can see the list of all my services that are inside my cluster. So right now I only have the petabridge.phobos.web. And I can take a look at all the operations that were recorded. These are the names of the different operations here. So I have an HTTP request right here, get, and that's the root. I have a couple of manual messages that I instrumented using my own C# code. And the rest of these were all basically recorded using Akka.net. So I can see some member exited, member left, member removed events. I can see some debug, disassociated event, and all this other fun stuff here. So let's go ahead and take a look at, an unhandled message, for instance, a unhandled message. So if I run a trace here, I can go ahead and see kind of the distribution of all these different traces and how they started. I can see they all began with this HTTP request right here. But each of these traces also includes at least one unhandled message. And I can see there's at least one error inside this trace. And this was recorded just a few seconds ago, and the total end-to-end processing time was 4.2 milliseconds. This is an example of a histogram that Jaeger can put together. And I can see where every single request starts. I see that it begins with a GET request, and that GET request was handled via Phobos Web 1. So I can see the host name of this node here. I can go ahead and see some logs that were recorded via ASP.NET here. And then I can see a custom little ask message right here. This is a custom operation that I recorded inside this application right here, where I went ahead and I grabbed my tracer and I called build span cluster.ask start active. So what happened was I basically sent this request to this router forwarder actor, which is going to go ahead and query another node inside the cluster possibly, and I'm going to await it. Well, when this await operation completes, or really I guess when this await operation completes, this span is going to get disposed, and that's going to go ahead and cause it to stop recording, which is how we end up with this long duration right here, that every other operation underneath this one has to complete first before this operation does. So I have this cluster.ask method here, and then I have an actor running still on Phobos Web 1, who's going to go ahead and receive. This actor is running at this location in my hierarchy. It's receiving a message of type string, and it's receiving that message from Akada cluster sys temp/c. By the way, this is all coming from Phobos, all this data. And I see some log messages that were recorded right here. And I can see that this actor took 133 microseconds to go ahead and process this work. So pretty fast. Then I can see down here another actor in Phobos Web 0. So this time the message actually jumped between nodes. So there was a whole layer of Akka.remote transmission that occurred under the covers here. And this actor, the /user/console, received this message from Phobos Web 1 and recorded some logs. And if I go ahead and step down through this, I can eventually get to my error, an unhandled message. Well, I can see the actor who didn't handle this message was the console actor, and it received this message from its child. If I take a look at the log right here, I can just see that that the message wasn't handled, and the message was this integer that was sent back to us, this int32 right here. And I can see up above, we actually received this message, but this actor was never programmed to handle it. So I could go ahead and figure out, okay, well, this actor received this message from this child actor down here, and I can see that that child actor was an actor of type phobos.web.childActor. I could go ahead and debug this message by either taking a look at this actor type or this actor type, the console actor. So right away, I can see these errors that show up, and I could go ahead and track them down by taking a look through my tracing system if I want to. I can also go ahead and take a look at, let's say if I want to take a look at an actor crash where an exception was thrown. I can see we've got, 6 errors right here. Man, what happened with this system? Well, I can see that we basically kept spawning that this actor right here, this actor.start, crashed 6 times in a row in the course of processing this message right here. And if I take a look at why it crashed, I go ahead and see that we threw an application exception, and I can see the trace right here. So this is really useful for our development teams. So for instance, here at Petabridge, we're using actors for running things like our recurring credit card transactions. We're using it for running things like fulfillment of some of the products people buy through SDK bin. We also use it for doing things like running email notifications when user subscriptions are about to expire and all that sort of stuff. Debugging a running system where we might have potentially hundreds of thousands of actors running at once would be extremely difficult to do using just a simple log system to go ahead and do that. Having a distributed trace available makes it so the developers on our team could go ahead and search for specific operations and figure out what was the root cause of these actor crashes or of, let's say, these timed out requests. I could also do something down here, for instance, where I want to say the minimum duration. Let's say a request that took longer than 10 milliseconds. Find traces. Well, I only have a handful of those. Okay, looks like we've got some that are even longer than 10 milliseconds, like 40 milliseconds. Maybe do I have any that are even longer than that? Let's see if I have a request that's longer than 100 milliseconds. Let's give that a try. I have one, and it looks like this is just when we received a log message here. So I don't know why that took 100 milliseconds. Looks like it only took 3 microseconds. So this actor might have actually been scheduled for a long period of time. Might have been what happened there. Oh, and here's an example of where we probably might have timed out up here, where we actually had a GET request that took 5 seconds for us to complete. There we go. So the distributed tracing system can also help us diagnose why some of these requests that appeared in the 99th percentile latency took as long as they did. So there's a lot of benefit to going and taking a look at this under the covers. Now, before we answer some questions, a couple things I want. One sort of outstanding one I want to anticipate is what about OpenTelemetry? Many of you may not have heard of OpenTelemetry yet, but this is going to be the new standard introduced in ASP.NET Core and .NET 6 for being able to keep track of HTTP metrics, to be able to add distributed tracing support. Because in case you didn't know, distributed tracing is actually now built into the W3 standard. So there's a set of standardized HTTP headers for doing that. So the .NET team has been working with the OpenTelemetry organization to provide a standard library that'll be able to gather this data in any type of .NET application. Problem is that it's not ready for production yet. It's in a release candidate status right now. We actually looked at using it last year as part of Phobos 1.0. I came to the conclusion that it's just kind of not quite there yet. But when .NET 6 comes out, which is the next version of .NET that's going to have long-term support, this will be available as part of sort of the library there. And it's all going to be built around the system.diagnostics.activity type that's included in the base class library. So eventually, we'll probably have to rejigger all of our presentations about metrics and telemetry for .NET and Akka.NET applications around OpenTelemetry, but that probably won't be until either really late this year or early next year. But this is kind of the next standard that's coming down the line here. So I want to thank everybody for their time today on the presentation. Hope you got some value out of it. If you'd like to learn more about Phobos, you can check out our website here. We have a whole bunch of tutorials and training videos on it. And I'm going to go ahead and answer the questions that were popping up in chat for the next few minutes here. But otherwise, thank you very much. I really appreciate your time today. Thanks for joining. Okay, so first question I'm going to go ahead and answer is from, let's see, Johan. Where are cluster node metrics coming from? Up, unreachable, and so forth. Those are actually coming from Phobos 1.1, which we just released last night. So you probably haven't had a chance to access that yet. So if I go ahead and pull up, let's see, SDK bin real quickly here. You know what? I'll just open a new tab here. Go ahead and open SDK bin. If I go to Browse Products, go to View Packages, Phobos.actor. So I added our release notes. I wrote these in Markdown, but they're not formatted that way on SDK bin yet. Basically, we now go and publish a number of metrics in Prometheus about cluster membership status. So I go to Prometheus here and I type Akka cluster members, execute. You'll go ahead and see that we basically have these statuses that are published in every node that counts the number of down, exiting, joining, leaving, removed on there. So that's where these are all coming from. And I basically just go ahead and aggregate those together. I think I do sum by, or maybe group by, I think it's cluster role, or is it host that I do that? I think I do it, no, maybe it might be Akka address. And that should get me my totals. Yeah, so I can basically go ahead and see that all these nodes are currently up. I should also go ahead and do, I think it's, you know what, dang it, I keep forgetting the names of these labels. Execute and status. There we go, that's the value I wanted. Akka address and status. Oh, gotta close my parenthesis first. All right. Actually, maybe I should just do this. Okay, well, apparently that didn't work. So I don't remember how I engineered this in Grafana anymore. Let me take a look at it. I think I did it this way. Okay, yeah, here we go. So I went ahead and just aggregated it by status like that. Yeah, so that'll go ahead and tell me how that's 3 up members. And I can go ahead and basically count. I basically go ahead and break this out for every individual status if I want. Okay, next question. Does app startup depend on Jaeger to be ready and working? I hope I answered it, but the answer is no. That would be an anti-pattern, and we want to try to avoid that. So in our case, if I scroll down here, if I scroll up to here, if the Jaeger endpoint environment variable is null or empty, then we're going to go ahead and try to go ahead and create a UDP port, a UDP sender down here. And if there's no UDP sender on the other line, no one's going to bother, no one's going to complain because it's just being fired via a UDP socket. Okay, next question. Go ahead and answer this one live. I have a question regarding performance implications using Phobos 1.0. Experienced a large degradation in a performance system that's become painfully slow. I think I just got a support ticket from your company actually about this. So yes, Phobos does have some performance impact as a result of its tracing and its metrics overhead. And we document some of this over here on this page, the performance impact of it. And we go ahead and basically give you a comparison of here's how expensive a fully instrumented actor is versus an actor that's not instrumented. One of the things you have the ability to do, if you want, is you can turn off monitoring and tracing for certain types of actors. And you can do that if I go into my little sample here. If I go to my Akka service where we create these actors, I could go ahead and say, all right, this child actor, I go ahead and say with instrumentation down here, new Phobos actor settings. And I can go ahead and say tracing off, monitoring off. And that'll go ahead and basically completely exclude that actor from tracing or monitoring. And that should help improve your performance there. Now, generally speaking, we want to go ahead and try to improve the performance of all of our infrastructure that we deliver. We do this routinely for Akka.net. We, of course, also want to do it for we also want to go ahead and make sure that we do this for Phobos as well. So if you can send us back any sort of, let's say, profiling data that goes and shows us where the startup overhead might be, we'd be happy to go and fix it. A lot of the times it's simple stuff that we can go ahead and fix that'll make these things that much faster. Okay, next question. How does the time callback stuff cope with async functions? Well, that's a good question. If I go back to, let's say, for instance, so I'll go ahead and answer this question live. If I go back down here, so we're actually using a timer to measure duration right here. By the way, if you ever want to manually get a hold of the instrumentation in Phobos, you can do it this way. By typing context.getInstrumentation, I can access the monitor that I'm going to use for recording metrics, or if I really want to, I can do, oh, never mind, there's actually a sample down here that does it. I can do context.getInstrumentation and grab a hold of the tracer that Akka.net is using. And I can go ahead and basically build a span and start it right here. That's going to allow me to go ahead and keep track of this underlying operation. So you can always go ahead and get a hold of that. Now, the way this works typically is for tracing at least, if I go back to program.cs, or excuse me, startup.cs, if I scroll down to our ASP.NET Core call, where we're actually running a trace, and we have, let's say, at least 2 different requests here, what's going to actually occur under the covers in terms of how we record this stuff is we go ahead and we stick the current active span inside an async local context inside the scope manager here, and that's going to be kept open. So we basically record the start time according to the system's local clock. And then when we dispose the scope that the span is in, we go ahead and we record the end time. And then we go and report that back to a tracing aggregation system like Jaeger, and it computes the total. So in the event that, let's say, we had a large number of asynchronous operations running behind the scenes, and it took us a while to get scheduled, that delay in scheduling would actually be reflected in the span that got reported back to a distributed tracing system like Jaeger. And we actually want that because this allows us to go ahead and experience it from the end user's point of view, because the end user really experienced that latency. Therefore, if we're running into, let's say, scheduling problems because the thread pool is so busy, we want that to be reflected in the metrics we capture as well. I believe that is also how timings and App.Metrics are recorded too. That it basically records a start to the metric, and then when we return back to the scope via the await call, we can go ahead and dispose that metric, and that'll record the total duration that lasted when we're running code like this down here, when we're going and recording a timing. So that's what's going on under the covers there. Let's see, next question. Do you have any recommendation on trace sampling in Akka.net, given that it can, actually let me answer this live. Do you have any recommendation on trace sampling in Akka.net, given that it can get quite chatty over a big cluster? Yes, I do. So if I go to Jaeger tracing here, and I pull up their documentation on their performance tuning guide. Well, I think this is mostly talking about your backend stuff. But on the client side, you want to go ahead and adjust the sampling configuration. So there's a couple of simple ways of doing sampling. One is using what's called probabilistic sampling, which uses a percentage. And that has to be configured somewhat statically at the time you go and create the tracer. So a probabilistic sampler might say things like include 10% of all tracing. All right. Well, we actually have some sampling strategies that are a little bit more sophisticated, such as we can perform a rate limiting sampling strategy, and I believe there's another one where, let's see, I'm trying to remember which one we go ahead and define up here. But the rate limiting strategy, the way this works is it's dynamic, where the Jaeger client is actually going to be talking over UDP to the Jaeger agent, and the agent's going to start recording as things get busy. It's going to say, hey, the volume of traces you're recording is getting huge. And it's going to go ahead and tell you to go ahead and slow down and stop recording as many. So what I would probably do inside Akka.net is I would probably go ahead and use a rate limiting strategy. By the way, other tracing libraries, like I believe Azure Application Insights is supposed to support something like this under the covers there. So this is kind of a more common strategy because you need it for really big applications. The other thing you can do in Phobos that I strongly recommend, I don't believe I have a demo of it in this application, but one of these Phobos lets you do, because this is a problem that's really specific to Akka.net, is we can actually go ahead and support a message filter down here. We have include and exclude message filters. So if I want to say I'm going to do an include message filter, it's going to say, okay, I want to go ahead and make sure I include all messages of type T. Well, one thing I could do if I really wanted to limit my traffic in here is I could do an exclude message filter of type object, and I could do an include message filter of type string, which basically means that I'm going to exclude all traces that satisfy this filter unless they satisfy this one. And so what happens in Akka.net is when an actor receives a message of type string for the first time, it's going to go ahead and begin a new trace. If an actor receives a message that already has a trace associated with it, it's going to continue that trace. So that way you can still trace the end-to-end lifespan of your request, but you're not going to be going ahead and creating a ton of, let's say, little small micro traces under the covers. So that's one thing you can go ahead and do under the covers. Okay, another question. What if security-based logs or messages? Does this follow observation? So security logs or messages, does this follow the observability or logging? That should really fall under logging. If you start seeing, let's say, all security problems showing up, good example, let's say you're working with a credit card processor like Stripe behind the scenes, and you start getting notifications that credit card transactions are being rejected because of, let's say, a high risk of fraud. Stripe might have a probabilistic model for detecting that. You'd want to go ahead and monitor that as an op metric inside your dashboard somewhere, because that might mean that someone's trying to use, let's say, your backend for taking a whole bunch of stolen credit cards and testing which ones go through and which ones don't. That's actually a pretty common problem in e-commerce. So I'd probably include that there. Now you could also trace that data as well, just to go ahead and see maybe which user was submitting all those requests. So you could use a combination of both to address some of those security problems there. Let's see, next question. Start span works fine in an async context, but there's the time method that accepts an async callback. Is there any point in using time at all for recording spans? So the answer is, so basically the question there is, does it make sense to go ahead and record durations in a system like App.Metrics or Prometheus if we're already capturing that data inside a distributed tracing system? The answer comes down to how you want to use that metric. If you want to be able to fire alerts based on those durations, or if you want to be able to go ahead and fire, if you want to go ahead and be able to, let's say, fire, well, I don't know, questions about, basically has the latency increased or not, you'd want to go ahead and use the timing method to capture that. I personally don't really mess with it. I'll keep track of the end-to-end latency in some of my HTTP requests, which I believe is done via a timing system. But I don't care about measuring the other small times between there because my tracing system will answer that question for me when I need it to. So I tend not to bother with that so much. Last question. Hi, Aaron. Prometheus seems to be failing. Its Windows service gets paused when large amounts of data are coming in. Do you know any workaround? Off the top of my head, this would probably be an issue um, with the number of, trying to think, this would probably be a file permissions issue where for some reason it can't rotate the time series database under the covers. So I'd go ahead and take a look at that behind the scenes. I forgot to click answer this live. Sorry about that. I'd go ahead and take a look at that. It's also possible that you might have some other limitations that are being imposed on disk. So I'd go ahead and take a close look at your Prometheus settings there. It's highly tunable and configurable, but that kind of sounds to me a little bit like it's a not necessarily a performance issue with Prometheus, but might actually be an access issue. Um, the other issue might be possibly you might want to lower your data retention settings. This is an issue that we ran into with Seq quite a bit for doing log aggregation, where we were not able to go ahead and store as logs as far back as we wanted because the volume of data being produced was excessively high. So as a result of that, we decided to go ahead and retain our data in Seek for no longer than I think 15 days for production and 3 days for all other environments. So that was something that we had to do to kind of avoid similar problems in our Seek system in production. Okay, let me just check YouTube for any questions. Is the problem with the debug break in a cluster node resolved? No, that can still be a problem where if you go ahead and debug one node with a Visual Studio debugger, that can actually cause disassociations everywhere else. Um, it is solved to an extent, which is that it's not going to blow up your TCP connections, and we have a 2-minute grace period before disassociation errors stop firing. But we still have a limitation where the cluster heartbeats are going to fail after a period of time, and that node will be marked as unreachable. So ideally, we would probably need to have a system that detects when the Visual Studio debugger is attached and just greatly increases all the timeouts there. But we have to increase those timeouts for every single node inside the cluster. That's one of the limitations there because the debugger is actually pausing the entire process, not just the thread of execution you're currently looking at. Okay, well, thank you everyone for your time today. I really appreciate it. If you have any further questions about monitoring or tracing or logging with Akka.net, you can always go ahead and reach us at petabridge.com. And please go ahead and check out Phobos if you liked what you saw today. That should really help you be able to get some visibility into your Akka.net applications at a fairly minimal amount of effort. So thank you very much for your time today. I appreciate it. And thanks for supporting us. All right. And thank you everyone on